This is series solutions of differential equations, and then in this video we're going to be talking about power series and analytic functions. We're going to begin with power series. So a power series about the point x naught is an expression of this form. So we have a sum from n equal to 0 to infinity of a sub n multiplied by x minus x naught raised to the n power. And of course you can see that expansion right here. X is a variable and the a sub n's are constant. Now we will say that the power series converges at the point x equal to c if the infinite series of real numbers, this sum a sub n c minus x naught raised to the n, converges. That is, that the limit of the partial sums exists. If this limit does not exist, the power series is said to diverge at x equal to c. Now, when we talk about a radius of convergence, for each power series of this form, there is a number, rho, and rho is between 0 and infinity and can be equal to both of those. And this is called the radius of convergence of the power series, such that the series converges absolutely for x minus x naught, absolute value less than rho, and diverges for x minus that x naught greater than rho. Now, if the series converges for all values of x, then rho is equal to infinity. And when the series converges only at x naught, then rho is equal to 0. And we are talking about this equation 1, this power series, definition of the power series. Actually, that's not. It's this that we're talking about. Okay, so let's take a look at this. So we have this interval. Power series always converge at the center. Sometimes we have a series that converges only at the center. Sometimes we have a series that converges on an interval. And sometimes we have a series that converges on the entire negative infinity to infinity. So we just have these different cases. Now, we're going to talk about the ratio test. And you may have seen this similar limit in the past. And you might have seen this a sub n and this a sub n plus 1 in a different place. This is just a different definition. This is a little bit different than what you've learned maybe in calculus. And here we say that the limit as n approaches infinity, and we have a sub n divided by a sub n plus 1, so that would be the next coefficient, is equal to L. And L is between 0 and infinity, including 0 and infinity. And if that limit is equal to L, then the radius of convergence is this rho that is equal to L. Let's go ahead and try one of these. We're going to first look at the convergence of this power series shown here. So we note that a sub n is equal to 3 to the n divided by n factorial. That's this a sub n right here. So we're going to take the limit as n approaches infinity of a sub n divided by a sub n plus 1, the absolute value. And that's the limit as n approaches infinity of 3 to the n divided by n factorial multiplied by n plus 1 factorial over 3 to the n plus 1. So you can see here that this is the limit as n approaches infinity of, and we'll go ahead and stack those like factors. And as you can see, we have here, we just have n plus 1 divided by 3, and that is equal to infinity. Therefore, our radius of convergence is equal to infinity, and our interval of convergence is negative infinity to infinity. Let's take a look at another example here. You can see that we have a sub n here, and this here, the center was 0. The center of this power series was 0. Here our center is 3. Okay, just to point that out. Okay, so we see that we have a sub n is equal to 4 divided by n squared plus 2n. And we're going to take the limit as n approaches infinity of the absolute value of a sub n divided by a sub n plus 1. So a sub n plus 1 is going to be n plus 1 squared plus 2 times n plus 1. And we're multiplying the reciprocal. So this is 1 divided by a sub n plus 1 is what this term is right there. Okay, and then all of that is divided by 4. Okay. Let's see. Okay, so now we have the limit as n approaches infinity, and we will go ahead and write our n plus 1 squared plus 2 times n plus 1 divided by, since our 4's will cancel, divided by n squared plus 2n. And as you can see, we're going to end up with the highest power in the numerator as n squared, the highest power in the denominator as n squared. So this limit is actually equal to 1, and that is equal to L. So our radius of convergence is equal to rho, and that's equal to 1. Now, we do have a couple things we need to look at, and I probably should not have written so big, so let me just go ahead and put that this is equal. I'll just leave that, but that's equal to rho, okay? So now, let's go ahead and take a look at what we have. So basically what we have now is that we will converge absolutely when the absolute value of x minus 3 is less than 1. So we have negative 1 is less than x minus 3. So x is going to be equal to, x is going to be between 4 and 2. So we know we converge absolutely for x between 2 and 4, but we do need to check those endpoints before we give our interval of convergence, okay? We do know here that our radius of convergence is equal to 1, and we know our center is 3. So this is kind of cool because this is 4, this is 2, and we are definitely convergent here. But what about at 2, x equal to 2 and x equal to 4? So that's why we need to check our endpoints. Okay, so let's go ahead and check x equal to, so we're checking the endpoints of that interval. Let's go ahead and check x equal to 2, plugging that in. We'll have the sum of n from n equal 1 to infinity of 4 divided by n squared plus 2n. And now we're going to have 2 minus 3 to the n power. And that's going to give us 4 divided by n squared plus 2n. And that's going to be negative 1 to the nth power. So this is convergent by the alternating series test. And you may need a little review of some of these convergence tests. We do keep it a little bit basic here. So now let's go ahead and check our other endpoint, which would be x equal to 4. And you can see we have the sum from n equal 1 to infinity of 4 divided by n squared plus 2n. And now we're going to have 4 minus 3 to the n. And so that's equal to n equal 1 to infinity. And that's just going to be 1 to the n. So we have 4 divided by n squared plus 2n. And of course, this is convergent by comparison to the p-series test. P equal to 2. Okay, so we're convergent at both endpoints, at x equal to 2 and x equal to 4. And therefore, our interval of convergence is the interval from 2 to 4, including 2 and including 4. Okay, what if we want to represent the sum and the product of power series? How are we going to add these together and find the product of these? Well, given two power series f and g as shown here, with non-zero radius of convergence. So we need to make sure that the radius of convergence is not 0, that the power series does not only converge at center. We want to find a power series representation for the sum, the product, and the quotient of the functions. And really, we're just going to be looking at the sum and the quotient in this sum and the product in this lesson of f and g. And the sum is simply obtained by term-wise addition. And you can see that here. So I kind of put the sum and the product together, but basically this is term-wise addition. Now, taking a look at the product, we can see the formula here. And one thing I want to make note about the product is that we will treat these power series as long polynomials and then we will apply the distributive law and then this is important, and then group the terms in powers of x minus x naught. It's not going to be that different, but that difficult, but we will definitely be able to come up with these products, and it won't be too complicated. Okay, so let's go ahead and look at the sum. We first have a sum here that we're looking at, and so we were given both f of x and g of x. So we do want to make note that we have n equal 1 to infinity for g of x, but the sum beginning at n equal to 0 index for f of x. So we do need to work on these indexes for a moment. So let's take a look at this. So for our index for f of x, we're going to go ahead and just let n approach k, okay? And so in that case, we're going to have f of x equal the sum from k equal to 0 to infinity of 1 divided by k plus 1 x to the k power. So we're going to match these indexes. However, for g of x, this time, as you can see, n is equal to 1. We're going to let n minus 1 approach k. So now we're going to have g of x is going to be equal to the sum from k equals 0 to infinity. And so now let's talk about this for a minute. If we let n minus 1 approach k, so n, let's write this down, n minus 1 is equal to k, so n is equal to k plus 1. And I also want you to see that when n is equal to 1, k is equal to 0. So that's what we're going to have right here. Okay, so now we have, let's go ahead and put this in. We have 2 to the negative n. So take a look here. Negative n, I think I want to write this in orange. Negative n is the opposite of k plus 1. So this is going to be 2 to the opposite of k plus 1. You can see that right here, to the negative n. And then multiplied by x to the k power. And we said x is to the k power because n minus 1 is equal to k. Well, now we're set up to go ahead and add these functions together now that we have matching indexes. So let's do that. So now we're going to say, therefore, f of x plus g of x is equal to, here's our f of x, and here's our g of x, and now we can say that this is equal to the sum from k equals 0 to infinity, and we're just going to factor out an x to the k and have 1 divided by k plus 1 plus 2 to the negative k. Let's just distribute that negative, all multiplied by x to the k. And we could probably go ahead and do this around that entire sum. Okay, now that was the sum. Now let's look at the product. So we are going to be looking for the first 3 non-zero terms in the power series expansion for the product. So taking a look at this first function, we can write out some terms, and we did mention this, that we would be doing this using the distributive property after we treat them as long polynomials. So we're going to plug k equal to 0, k equal to 1, k equal to 2, or you may already know the power series expansion for the sine of x. And so here, of course, we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so forth. Of course, the sign of x is an odd function. That's always helped me remember that. Just a beautiful pattern. And likewise, the cosine of x, beginning with plugging in a 0 and so forth, you would come up with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so forth. So now if we're going to find the product, as we mentioned earlier, we're going to be using the distribution property, and then we're going to be gathering terms of x minus x naught, and in this case it would be x. So here is our g of x, and we're going to multiply it by, f of x, and we're going to multiply it by g of x. Okay, and so now we're going to look at these terms. We're going to look really, really closely. In order to gather our x's, we can only get an x from the x times the 1. That's the only place we're going to get that. So our first term is going to be an x. Now we're going to gather some terms of x cubed, because we will never get an x squared, because this x will go to the 1 multiplied by the 1, and then it's going to be an x cubed term. We're also going to have a 1 multiplied by this x cubed term. So there's only 2 places that we can come up with an x cubed, and that would be multiplying this by 1 and multiplying x squared. Whoops, I was going to do that in another color, x squared by x. Okay, along with the constants. Okay, so let's go ahead and take those. So now I'm going to use parentheses, and I'm first going to write a negative 1/2 from this term, and then I'm going to have a negative 1/6 from this right here. And those will be my x cubed terms. I wrote those awful big. Negative 1/2 minus 1/6. And those are my x cubed terms. And now we're going to come up with our x to the 5th terms, because that's going to be the next. And how are we going to get an x to the 5th? We're going to get an x to the 5th of this term multiplied by 1. That's going to be our first. The second is when we're going to get x cubed multiplied by this x squared. And there's one other place that we're going to get x to the 5th, and that's going to be this x term multiplied by this term. Okay, so we're going to factor out x to the 5th. So there's 3 places. So let's do that. We're going to factor out an x to the 5th. And let's go ahead and take that. The first that we're going to get is going to be this x multiplied by this one, and that's going to be a 1 divided by 4 factorial. And then we're going to add this term and this term multiplied together. So that's 1 over 3 factorial. And I'm just going to wait on this x to the 5th because I don't know how much room I need. So we had 1 over 4 factorial, and now we have 1 over 3 factorial multiplied by 1 over 2 factorial plus, and now we've got this term, which is 1 divided by 5 factorial. And those are going to be my x to the 5th terms. And we just needed the first 3 non-zero terms. So let's just simplify this. This is x minus 2/3 x cubed plus 2/5 x to the 5th. Okay, let's take a look at our next product. Here we're given e to the x multiplied by e to the negative x. And you can probably already think about what that's going to be. So it's just something that, of course, we would know here before we start, but let's go ahead and show that. Okay, so our f of x is going to be equal to, let me just use a different color pen, plugging in a 0, 1, 2, 3, and you already may know this for e to the x, 1 plus the power series, x plus 1/2 x squared plus 1/6 x cubed plus so on and so forth. And this g of x, e to the negative x, is 1 minus x plus 1 over x squared minus 1/6 x cubed, and so on and so forth, okay? So I want to do the same method as far as gathering terms and things like that for this product because it's quite interesting. So let's go ahead and do that. So we're going to have f of x multiplied by g of x, and it's going to be x plus 1 plus x plus 1/2 x squared plus 1/6 x cubed, all multiplied by, I'm going to go ahead and erase this just so I can move this over. But we do already see why we're going to have that. Okay, so now we have a little more room to work with. One minus x plus 1/2 x squared minus 1/6 x cubed, and so on and so forth. Okay, so remember we're going to gather our terms here. So the first thing we're going to get is a 1 times a 1. I mean, that's the only way we're going to get that first term. So we have that to be 1. Now we're going to go ahead and gather our x squared terms. So to get an x squared, we will have an x times an x, or we will have a 1 times this term. And we will also have, yes, we will have that. Okay, so for our x terms, I hope I didn't miss that, we will gather, whoops, so we will have a plus, and now we will have a 1 times a negative 1 plus a 1 times a 1. So we have a 1 times a negative 1, and then we're going to be adding that to a 1 coefficient multiplied by this 1. And those are going to be our x terms. Let's do the same for the x squared. So for our x squared terms, we are going to have 1 times 1/2 plus 1 times 1/2 plus a negative 1 multiplied by a 1, and these are going to be our x squareds. I'll show these to you. So we have a 1 times a 1/2. We have a 1 times a 1/2. And we have a negative 1 multiplied by a positive 1 times x. So those are our x squareds. And then for our x cubed, whoops, we will have a 1 times a negative 1/6 plus a 1 times a 1/6 plus a 1 times a 1/2 plus a negative 1 multiplied by a negative 1/2, and these are our x cubes. Okay, and those came from, you can just go ahead and check that out, but here is our 1/6 times a 1. Here's our negative 1/6 times a 1. Here's our 1 multiplied by a 1/2, and so on and so forth, and you can check those. Okay, so these are our first 3 non-zeros. So let's see what we have. Well, this is a 1, but this is a negative 1 plus a 1. That's gone. This is a negative 1 plus a 1/2 plus a 1/2. So that's 0. So all of these terms go to 0 except for that 1. So this goes to 0, this goes to 0, and that goes to 0. So we just end up with 1. Okay, let's talk about power series vanishing on an interval. So if the sum from n equal to 0 to infinity of a sub n times x minus x naught to the n is equal to 0 for all x in some open interval, then each coefficient a sub n equals 0. Okay, and differentiation and integration of power series. So basically, if this series has a positive radius of convergence, then f is differentiable on the interval x minus x naught is less than rho, and term-wise differentiation gives us this power series. So we will be differentiating term by term, and here is f prime. And as you can see, we just take this n and bring it to the front, which is what we did here, and then we take this to the n minus 1 power, which is what we have. So it's just really our power rule on this series. Okay, integration is the same. It's a little bit more technical, but of course we have to have that positive radius of convergence, and the integration is the same. So you add 1 and divide, and you can see that right there, just like our typical integration of power series. Okay, so let's just jump right in. We're going to find a power series expansion for f prime of x for this sine of x function. We will just assume that this series has a positive radius of convergence. Okay, and so let's go ahead and take a look here. We have that the derivative is going to be equal to, and this first, this negative 1 to the k and the 2k plus 1 factorial, that's just a constant. So that is just part of the taking the derivative. So now we'll bring that 2k plus 1 to the front, and we have x to the 2k plus 1 minus 1. So we just have 2k. And so now we can go ahead and simplify that a little bit. So you can see that we will just have negative 1 to the k divided by, and when you can see here that 2k plus 1 factorial is equal to 2k plus 1 multiplied by 2k factorial. So now those 2k plus 1s will cancel, and we're just left with 2k factorial in the denominator multiplied by x to the 2k. And you can, if you recognize that, you will see that this is equal to the cosine of x. Okay, let's give another one a try. Let's find the derivative of this function given here. We will assume that the series has a positive radius of convergence. And let's just jump right in. So we have f prime of x is equal to the sum n equal 1 to infinity. And we have our n there already multiplied by, whoops, can't forget about a sub n. A sub n multiplied by n minus 1 power rule x to the n minus 2. Now I want to make note of something. Note that the starting index n equal 1 gives 0 for the first term. You can see that there, we're going to have 0 for our first term. Therefore, we will start the series. Really wanted to make that therefore a little bit nicer. Therefore, we will start the series at n equal to 2 to obtain the first non-zero term. Okay, so let's do that. So we will have f prime of x equal the sum n equal 2 to infinity, and we will just have n, and I'll put that n minus 1 right after that, a sub n x to the n minus 2. Okay, let's try some integration. We're going to find a power series expansion for g of x that is by definition equal to the integral from 0 to x of f of t dt. Let's check and make sure we have a positive radius of convergence, and we'll use that ratio test. So we have that rho is equal to the limit as n approaches infinity of negative 1 to the k divided by 2. And I'm going to go ahead and put n's here. Divided by 2n plus 1. And then now we're going to have 2n plus 3. And I'll explain that in a minute. Negative 1 to the n plus 1 power. So we do want to keep in mind that 2 times n plus 1 is 2n plus 3. So that's the next, that's for n plus 1. Okay? And so now we get that that's equal to 1. So rho is equal to 1. So we can proceed with term-wise integration. Okay, so let's do that. So we know that g of x is going to be equal to the integral from 0 to x of this sum k equals 0 to infinity of negative 1 to the k divided by 2k plus 1 factorial multiplied by t to the 2k dt. So if we integrate that, we're going to have, make that a little bit big, we're going to have that that's equal to the integral from 0, no, we're going to go ahead and integrate. Let's go ahead and integrate that. So now we have the sum from k equals 0 to infinity of negative 1 to the k divided by 2k plus 1. That's just a constant. So now let's bring our 2k plus 1 in the denominator multiplied by t to the 2k plus 1. Add 1 and divide, and we are going to evaluate that from 0 to x. And if you want to put all of that in parentheses, we can. So plugging x into that expression, we have the sum from k equals 0 to infinity of negative 1 to the k divided by 2k plus 1 factorial multiplied by 2k plus 1 all times x to the 2k plus 1 power. And if we go ahead and find the first few terms, starting with a 0, we're going to come up with x. And then our next term, plugging in a k equal to 1, we will come up with x cubed divided by 18. Plugging in a k equal to 2, we will have x to the 5th divided by 600, and so on and so forth. Okay. Let's take a look at shifting the summation index. I think we all know that this index of a summation in a power series is really just a dummy index. It's just like the variable of integration when we have a definite integral. So there are times we want to change the variable of integration. Well, now there are situations where we want to change or shift. So we will have situations where we will want to change or shift the index of summation. Okay, so these are pretty quick examples, but let's take a look at this. So basically, we are able to shift from n equal to 0 to k equal to 0 to I equal to 0 and so forth. And you can see that the subscripts a sub I, a sub k will also be shifted to or changed. So let's go ahead and take a look at this example. Express the power series as series with a generic term x to the k. So as you can see right here, we want this to be k. Okay, and maybe I shouldn't write that like that. So this is, we want k to be equal to n plus 2. Okay, so if we want k to be equal to n plus 2, that means n is going to be k minus 2. And we do need to make note that when n is equal to 2, when k is equal to 4. You can see that right there, okay? And that's going to help us. So we're going to need that bit of information to now say that this is equal to the sum from k equal to 4, right? When n is 2, k is 4. From k equal to 4 to infinity of k minus 2, because that's our n. This is k minus 2. And then n minus 1 is going to be k minus 3. And then we have a sub k minus 2. And now we have our x to the k. So all of that is really important to make sure that you follow along. Let's do one more. So what do we want n plus 3 to be? We want k to equal n plus 3. And if k is n plus 3, we know that n is going to be k minus 3. And with that, we now know that n equals 1 when k is equal to 4. Okay? So now, in coming up with this generic term x to the k, we're now going to have the sum. And remember, n equal 1, k is 4, just happens to be, again, to infinity. And we have a sub k minus 3, because that's our n, divided by k, because that's what n plus 3 is, all multiplied by x to the k. Okay, now let's come up with some Taylor series. Determine the Taylor series about the point x naught for the function. So we were given that x naught was equal to 0, and our function is the natural log of 1 plus x. So let's remind ourselves, for the Taylor series, what we're looking for is we're looking for the sum from n equals 0 to infinity of the nth derivative evaluated at x naught divided by n factorial multiplied by x minus x naught to the nth power. So we need some derivatives. So let's just go ahead and take a few. We have f of x equals ln of 1 plus x, and f of x naught is going to be 0. The natural log of 1 is 0. Let's find our first derivative. We have 1 over 1 plus x, and f prime at x naught is going to be equal to 1. F double prime of x is going to be negative 1 over 1 plus x squared. And we have that f double prime of 0 is a negative 1. And then let's find our third derivative, and that's going to be, well, that should have been an 1 plus x all squared. And then that third derivative is going to be a positive 2 over 1 plus x cubed. And f triple prime of 0 is going to be equal to 2. And that fourth derivative of x is going to be a negative 3 times a 2. You can see a factorial happening there in the numerator, divided by 1 plus x to the 4th power. And we evaluate the fourth derivative at 0, and that's going to be equal to negative 6. Okay, so we're going to be looking for a bit of a pattern here. So what do you see here? We see that we have the nth derivative of x, and we see this alternating term. So we have negative 1 to the n plus 1 because we are positive here and alternating. So we were positive on the first derivative. So we need that n plus 1. And then what do we notice? We see that we are also multiplying by n minus 1 factorial in the numerator. So we can see that this is a 3 factorial when n is 4, a 2 factorial when n is 3, and so forth. So that factorial is 1 less than n. And then we notice, and we can just put this under, we can put it under all of it. Then we notice that denominator is 1 plus x, and that is to the nth power. Now let's make a note. Since f of 0 is equal to 0, the first term of the series vanishes. So basically, we will begin or shift the index to start at n equal to 1. Now keep in mind that this is just this. We still need to divide by n factorial and multiply by that. Okay, all of this. So let's do this. Therefore, the Taylor series is going to be the sum from n equal 1 to infinity of negative 1 to the n plus 1 multiplied by n minus 1 factorial, all divided by, and I did want to make note here, if we evaluate this at 0, make this just a little bit smaller here. Evaluated at 0 is just going to be, we're going to lose this denominator term. I really don't have enough room here. I'll go ahead and bring this down, and we'll just write it right below it. Okay, and so that's where we come up with this, our Taylor series, and now we have our n factorial in the denominator, and then we have x minus 0 to the n power, so that's just going to be x to the n. Now we do know that n factorial divided by n, I guess I'll just have to move this whole thing. We can simplify that now. So we know that that is equal to the sum from n equal 1 to infinity of negative 1 to the n plus 1 power divided by n multiplied by x to the n. That is our Taylor series. And this is because, of course, this is because n minus 1 factorial divided by n factorial is n minus 1. Whoops. N minus 1 factorial divided by n multiplied by n minus 1 factorial. So these will cancel and we're just left with the n in the denominator. Okay, let's find the Taylor series about the point x naught for this polynomial. Again, we're going to need some derivatives. So if we have f of x equal x cubed plus 3x minus 4, we have f of 1 equal to, let's see here, that would be 0. So now we have f prime of x is equal to 3x squared plus 3, and we have f prime at x naught to be equal to 6, and we have the second derivative is 6x, and we have that second derivative evaluated at our x naught, and that's going to be 6, and our third derivative is 6, and our fourth derivative and all future derivatives are going to be equal to 0. Okay, so now let's take a look at this. We know for our Taylor series that we want the sum n equals 0 to infinity of the nth derivative, and in this case we're going to evaluate that nth derivative at 1 and divide it by n factorial and multiplied by x minus 1 to the nth power. That's what we want here. So we're going to go ahead and define this right here, and we're going to call that, let that be c of j, and that's going to be the jth derivative evaluated at 1 divided by j factorial. So let's go ahead and see what we have here. So taking a look at c sub 0 is 0. That matches this. We have c sub 1 is 6 divided by 1 factorial, which is 6. C2 is equal to 6 divided by 2 factorial, which is equal to 3. I'm just going to kind of put these under here, I think. So we have c sub 0 equals 0. C sub 1 is 6 divided by 1 factorial. C sub 2 is 6 divided by 2 factorial. C sub 3 is 6 divided by 3 factorial. And for all of our future coefficients, we have c sub j is equal to 0 for j greater than or equal to 4. So now we're going to put all of this together. So now all we have to do is multiply by this right here. So it's going to be c sub j our constant multiplied by that x minus 1 to the nth power, that constant, okay? And I'll just put an n here, okay? So that's equal to 6 multiplied by x minus 1 plus 3 multiplied by x minus 1 squared plus x minus 1 cubed. Okay, let's take a look at this one. F of x is equal to the square root of x. And here, x naught is going to be equal to 1. We're going to need some function values and derivatives. And I will just write some of these down. Okay, so let's do the same thing. Let's take a look at these coefficients. So all we need to do is divide these by n factorial. So we would divide this f of 1 divided by 1 factorial, 2 factorial, just to get that first, coefficient. So here we would have c naught is equal to 1. Here we would have c sub 1, and I have these factorials off. This would be 0 factorial, 1, 2, 3, and 4 factorial. And I think that divided by looks good. I probably should just write that. Okay, and so now we have this equal to C naught, and that's going to be equal to 1. And C1 is 1/2. C sub 2 is a negative 1/4. C sub 3 is going to be equal to 1/16. C sub 4, that would be divided by 4 factorial. That would be a negative 5 over 128. So now keep in mind that what we're looking for now is that we want the sum from n equals 0 to infinity of that nth derivative evaluated at 1 divided by n factorial, and these are our c's. Those are our c sub k's, or you could just call them c sub n's. Okay, but we still have to then multiply by x minus 1 to the n. And so that's what we're going to do now. We're going to have 1 plus 1/2 x minus 1 minus 1/8 x minus 1 squared plus 1/16 multiplied by x minus 1 cubed minus 5 over 128 multiplied by x minus 1 to the 4th, and so on and so forth. Okay, well, that concludes this video.